In figure 1.1, three blocks with masses of m, 2m, and 3m are connected and pulled to the right on a horizontal frictionless table by a force with a magnitude of F. Find the magnitudes of the tensions T sub 1 and T sub 2 in the interconnecting chords. Let's now review some key ideas that will be helpful in solving the problem. First is Newton's second law of motion. It says that the sum of all forces acting on a body is equal to the mass of the body times the acceleration of the body. In the problem, we were given forces and masses. So it might be helpful if we assume some form of acceleration in the solution of the problem. And the second idea that we might want to remember is that the tension in a rope or a string is the same throughout the rope or the string. And so whatever the direction of the force that we're looking at, if it is a tension, then it will have the same magnitude whichever direction we're looking at. Now, here we just draw a free body diagram. So the first step, the first free body diagram that I drew here is for the entire system. So we see the box there, that's our body. And we see that it's acted upon by a force. There's only one force, and that's F. And again, because we're going to be using Newton's laws, it's good to assume an acceleration. In this case, let us assume the acceleration to be A. So now Newton's laws of motion becomes the summation of all forces acting on the body, which is just this one. So it becomes equal to F, and F is equal to the mass, the total mass, which is m plus 2m plus 3m. So that's 6m times the acceleration that we assumed, which is just A. Next, we draw the free body diagram for the first block here. And again, there's only one force acting on it, and that's the tension T sub 1. And this time the direction is towards the right. And so if we write Newton's second law for this, again, it's just the summation of all forces acting on this body, and that's only T1. So that summation is equal to T1. And Newton's second law says that that summation is equal to the mass times acceleration of the body. So the mass of this body is m, and the acceleration is the same as the entire body, so that's A. And therefore, actually, from these two equations, you can see the relationship between T sub 1 and F already. Because 1/6 of 6m times A, which is the force F, then 1/6 of F is actually equal to the tension, the first tension, T sub 1. And actually, there's only one choice here that has this option, and so that's letter D. So we'll see that the answer would be letter D. But before we do that, let's just try and see if the second one is the same. So again, let's just draw the free body diagram, and this time there are two forces acting on this block. The force to this direction, T sub 1, and the force to this direction, the tension T sub 2. And Newton's second law says that the summation of all these forces, that means T sub 2 minus T sub 1, the summation of all those forces is equal to the mass times acceleration of this body. So if you write that down, the summation of all forces acting on this body is equal to, well, the summation is T sub 2, that's the first force, and the other force is T sub 1. And we do a minus T sub 1 because they're on opposite directions. And this is equal to the mass times acceleration of this body. So the mass is 2m and the acceleration is A. And so this becomes our equation. But we already know what T1 is, right? T1 is MA. And so we just move T1 to the other side and replace it with MA. And so we are left with T2 equals 3MA. And again, 3MA is 1/2 of F, which is 6MA. And again, that is consistent with letter D out here. Therefore, the answer to this problem is this bit here, letter D. In figure 1-2, block A of mass M is released from rest at a height of h, slides along a frictionless slope, and then collides with stationary block B of mass 3m. After the collision, block A stops while block B moves to the right. Find the coefficient of restitution between block A and block B. Just a review of some of the key concepts that we will need to solve this problem. First is the idea of relative speed. If we recall, the relative speed of an object is its speed with respect to another object. So for example, if we are in a train, we are inside the train and the train is moving, we and the train would have the same speed. So even if the train is moving, we will see that the things inside the train to be stationary because we are moving with the train, and so are the things inside the train. In that case, we say that our relative speed with respect to the train is 0 because we're all moving in the same direction, and that's why everything else looks stationary. That would have been different if we were outside the train and looking at the train as it passes through or passes by us. In that case, we are stationary and the train is moving at some speed, and so there is a difference in speeds there. And the relative speed, our relative speed with respect to the train would not be 0 in that case. The way we compute relative speed is pretty straightforward. We just get the difference in the velocities, and then we get the magnitude of that difference. That is the relative speed. Now, we had to review relative speed because the problem asks us to compute the coefficient of restitution. We call it COR in this problem, and the coefficient of restitution is defined as the ratio of the relative speeds after and before the collision. So that means we'll need to find the speeds, or rather the relative speeds after and the relative speeds before the collision. And one thing that is most or often useful when talking about collisions is the law of conservation of momentum. This is useful because it tells us the relationship of the speeds of the objects right before the collision and right after the collision. And more precisely, it states that if we have two objects of mass m1 and m2, and they are moving at v1 and v2, then the sum of their momenta would be the same before they collide. In this case, that is the sum on this side of the equation, and after they collide, that is the sum here at the right of the equation. So momentum is defined as the product of the mass of the object with its speed. In this case, velocity, more precisely, it would have been velocity, but in this case, it is speed because we're just concerned with the magnitudes in this problem. So this first term on the left is just the velocity times the mass. In other words, the momentum of the first object. And here is the momentum of the second object. And all these terms here are prior to the collision. Now, right after the collision, the velocity or the speed of the first object changes from v1 to v1 prime. So this is the new momentum right after a collision of the first object. And for the second object, this would have been the new momentum. And the conservation of momentum tells us that the sum of all the momentums prior to the collision would be equal to the sum of all the momentums after the collision. And in our problem, we only have two objects, so we will be using this form, but this is extendable to as many objects as we're interested. Now let's start computing for the coefficient of restitution that the problem is asking for. We need to find the relative speed before and after the collision. First, let's look at the relative speed before the collision. So let's call that relative speed v sub I. And here we made a drawing of the two objects. Here we have block A, and here we have block B, just right before the collision. So the problem is interested in the collision, right before it and right after it. So we can ignore, right now we can just ignore for the meantime, the fact that A is in this location at the beginning. So we don't even have to talk about what happens to A from this location to this location at the moment. We just need to talk about what happens right before the collision and right after the collision. So right before the collision, the mass of block A is m, its speed is v sub 1, so its momentum is just the product of that, and that's mv sub 1. And then the momentum of block B right before the collision is 0 because the problem states that it is stationary right before the collision. So its velocity or its speed is 0, even if its mass is 3m. So 3m times 0 is just 0. And so the relative speed right before the collision is just the difference. That's v sub 1 minus 0. And you take the absolute value of that and you get this bit here. So v sub 1 is just the absolute value of v sub, or rather v sub I is just the absolute value of v sub 1. Moving forward, we now compute the relative speed right after the collision. And let's call that relative speed v sub f. And again, we draw our blocks. This is again block A, and here is block B. And what changes are the following. The speed of block A would be 0 because it says in the problem that block A stops right after the collision. And so its momentum would also be 0. For block B, it starts moving. And so we assign it a velocity or a speed of v sub 2 prime. And its momentum would be 3mv sub 2 prime. That's just a product of the mass and the speed. Now, we can compute the relative speed after the collision, and that's just the difference, right? So v sub 2 prime minus 0, and we take the absolute value of that. From this definition of the coefficient of restitution, we can say that the coefficient of restitution is just the ratio of this expression to this expression. And now we just need to know the relationship between this and this. And we already mentioned that the way we do that is through the law of conservation of momentum, because that law relates the speeds prior to the collision and right after the collision. So the law states that the sum of the momenta prior to the collision is equal to the sum of the momenta after the collision. So before the collision, the sum of the momentums is just mv sub 1 plus 0. And right after the collision, that's 0 plus 3mv sub 2 prime. If we write that down, it will look like this. And we can easily rearrange this to give us this. And it says, so what we did there is we divided it with we divided it by m, both sides, and we saw that we can divide both sides by v sub 1. And then we take the absolute value, and we see that that ratio that we're looking for is 1/3. Therefore, this is the answer to the problem. A parallel plate capacitor has plates of area S in separation D and is charged to a potential difference V. The charging battery is then disconnected and the plates are pulled apart until their distance becomes D plus delta D. The vacuum permittivity is denoted as epsilon sub 0 or epsilon naught. Find the work required to separate these plates. Let's now review some ideas that will be helpful in solving this problem. First is the idea of work. We recall that work is the change in energy, in potential energy in this case, from one state to the other. So here we have the final state when the capacitor plates have been pulled apart, and here is the initial state before the plates were pulled apart. And then we also need to remember the energy stored in a capacitor, in a parallel plate capacitor. And in this case, the energy, the potential energy stored in that capacitor is 1/2 CV squared. C is the capacitance, V is the voltage across the capacitor plates. And we note that C is dependent, the capacitance is dependent on the separation of the plates. We call that separation D. And the voltage is also dependent on that separation. And so we just write it there to remind ourselves. And you might also recall that this can be stated in a different way. So C times V is just the charge stored in the capacitor. And in fact, that's how we define the capacitance. It's the constant that when multiplied by the voltage, we can get the amount of charge in the capacitor. So CV can be condensed into one variable Q, which is the charge stored in the capacitor. And now, in this case, Q is not dependent on the separation anymore because that's just the charges in the plates. And that's why we remove the D dependence there. And we are left with just a single dependence in V, and V remains dependent on the distance of separation D. Then we also recall the capacitance as a function of the geometry. In this case, the parallel plate capacitor. The capacitance is equal to this expression here. Here we have the coefficient of proportionality, which is the permittivity of free space in this case, and the capacitance is proportional to the area of the plates and inversely proportional to the distance that is separating the plates. Now we start working on the energy terms here so we can find the work. Let's start with the initial state. Here we have a separation D and then an area S, permittivity E naught or epsilon naught, and the total charge Q. And the energy stored in the capacitor, this capacitor, would be the following. So that would be 1/2 Q, which is the charge, which we know from here. And now we express this voltage as the product of the electric field across the capacitor times the separation. So we'll have to remember that the voltage is just the electric field times the separation there. Or in other words, the electric field is the ratio of the voltage to the separation, that capacitor. And this is neat because the electric field is not dependent on the distance here. And so this is a very good form. Q is not dependent on the distance. E is not dependent on the distance. Only D here is, well, the distance. And so we can also find the energy in the final state very easily using this. And in fact, we just replace the D with D plus delta D. So we obtain the following expression. And now we just have to subtract the final energy, which is this case, this is the final potential energy, and subtract from it the initial potential energy, which is this. So you see that the subtraction will be rather simple. Now we carry out the subtraction. So again, the subtraction would be like this, and clearly the D here and the D here would cancel each other, and we're left with this. Now this is a correct answer. However, these variables are not in the choices, so we need to express Q in terms of these variables and E, or electric field, in terms of these variables. So Q is simple because we recall the definition of capacitance is that it is the constant that when multiplied by the voltage results in the charge, the amount of charge, and Q is the amount of charge. So we can replace this with the product CV. And then the electric field, we recall the relationship between the electric field and the voltage. We note that the electric field is the ratio of the voltage to the distance separating the plates. So we can replace E with the following: voltage over D, and the charge Q can be replaced with the capacitance times the voltage. And then we're getting closer to the variables here, except that C here does not appear in any of the choices. So we need to express it in terms of the other variables in here. And this time we use this third idea here. C is known to be in a parallel plate capacitor. We know that the capacitance is proportional to the area of the plates, that's S, and inversely proportional to the distance separating the plates. Again, that's D. And the constant of proportionality is epsilon naught. So we replace the C here with this bit here. And this is what we get: 1/2 epsilon naught, and then the S over D, that is from this first bit of the equation. And then the V and the V here combines to V squared and delta D, and we have another D here. And just simplifying this, we obtain the answer. And that answer is this, which is letter F in the choices. A sinusoidal wave travels in the positive x direction with a constant speed of 0.30 meters per second. Figure 1-3 shows a snapshot of the wave at t equals 0 seconds as a function of x. The wave is reflected at a fixed end at x equals 0.90 meters. Find an appropriate graph for the wave at t equals 0 seconds from figure 1-4. So figure 1-4 is not here, it's in the next slides. It's just the figures that contain the choices. Let us now consider a few ideas that will be useful in the solution of this problem. First is the idea of wave reflection. So wave reflection of a fixed end means that the reflection is 180 degrees out of phase. What that means is that the wave is flipped vertically. If we start with a wave like this, after it reflects off this end, fixed end, it will now look like this. So the negative portion now becomes positive, and the positive portion now becomes negative. And if you think about this in terms of Newton's law, so if you have a string here and you have a fixed end here. When the wave reaches this boundary here, so there is a reaction. So it kind of pulls the boundary upwards. And so the boundary also pulls it downward. And so when it reflects, that downward pull is what manifests. So it goes this way. And that happens to every other point that follows. So when you are here, the pull is quite strong, and so you also have a pull downwards that's quite strong. So that's kind of an intuitive way of understanding why this is the case. The other idea is the idea of superposition of waves. This means that if you have two waves, when you try to put them on top of each other, they will just add algebraically. So for example, if we have these two waves here, this is negative here and this is positive here, if they were all of the same absolute values in the y direction here and here, then when you put them on top of each other, they will cancel out and they will become zero. On the other hand, if they had the same sign, so for example, if you had this wave and you add it to itself, then the resulting wave would just be twice the original. That's what we mean by superposition of waves. We just add them algebraically. The problem is asking us to imagine what happens after t equals 2 seconds. So to make it easier for us, I put a star at the beginning of the wave. So that's going to help us track the wave, the motion of the wave. So after 2 seconds, the wave would have moved. By how much? That would be dependent on the amount that is indicated in the problem, that is the speed. So because it moves at 0.30 meters per second, after 2 seconds, it would have moved by this amount, 0.3, which is the speed, times 2 seconds. And now that's 0.6 of a meter. And so after 2 seconds, the star would have been translated 0.6 of a meter. So from here to here. And in fact, the whole wave would have been translated. So it moves from here, and then now it becomes like this after 2 seconds. However, we see that there is this portion here, this bit here, that doesn't happen. This will not happen because we have a barrier here where reflection occurs. So we said that during reflection, this wave actually gets flipped. And so the reflected wave would have looked like this. And we're only concerned with this second portion because only the second portion will be reflected. So we can ignore for a moment the first part of this green reflection. So looking at the second portion, which is this reflection, now it will be reflected, it would go like this. So now we only have this portion of the wave. So the red bit is from the first part of the wave. The green bit is from the reflection of the second part of the wave. And what that tells us is that the resulting wave would now have only this portion. Therefore, that means that we will have double this portion here. If you look at the choices, the doubled downward or the doubled opening upward portion is only this bit here, right? It doubles from 0.3 to 0.6. And therefore, the answer to this problem is this one. An ideal gas undergoes the cycle shown in the PV diagram of figure 1-5. Find the net thermal energy added to the system during one complete cycle. Let's review some ideas that will be helpful in the solution of this problem. First is thermal energy. Thermal energy is the kinetic energy, the average kinetic energy of the particles in the system. And so the faster and the more massive the particles are, the more kinetic energy there is. And we can actually measure the average kinetic energy of the particles using a thermometer. The temperature is known to be directly proportional to the average kinetic energy of the particles. We're not going to show it here, but we'll have to keep that in mind. And that is a well-known fact from statistical mechanics and thermodynamics. So temperature is a measure of the kinetic energy, the average kinetic energy of the particles in the system. Next is the first law of thermodynamics. It says that the change in internal energy of the system, change in the internal energy of the system, equals the amount of heat coming in the system minus the work done by the system to its environment. So that's the work coming out of the system. And here, the heat in, this term here, is what actually adds to the thermal energy, because it's the heat here that actually raises the temperature, thereby raising the thermal energy or the kinetic energy, the average kinetic energy of the particles. And then we also recall that internal energy is a state variable. So internal energy is the sum of all the energies of the particles in the system. So it's in the micro scale. Each particle will have a kinetic energy, potential energy associated with it, like chemical potential energy, electrostatic potential energy. So the sum of all those energies, both kinetic and potential, that is what we call the internal energy of the system. Now, internal energy is known to be a state variable. That means that it depends only on two other state variables, which is temperature, volume, and pressure, any two of those. So in this problem, we're dealing with pressure and volume because it's a PV diagram. And what that means is that the internal energy of the system depends only on the P and the V. And the corollary is that in one thermodynamic cycle, any thermodynamic cycle, the change in internal energy would have to be zero. The reason for that is a cycle is one where you begin at a certain pressure and volume, certain P and V value, and then there are several processes in the way, and then it goes back to the initial P and V values. That means it goes back to the initial state. Now, we have said that the internal energy is dependent only in the P and V values. So if you have a cycle, the initial internal energy is the same as the final internal energy, because the initial P and V value is the same as the end P and V value if it's a cycle, because that's what a cycle is. The initial P and V value must be equal to the final P and V value. And because they're equal, internal energies are equal at the beginning and at the end, then there is no change in the internal energy. So this term here actually goes to zero. That's what we'll use in the solution. And lastly, we'll have to think about PV work because we have a work term here, and that is known to be the area under the process curve. So if you have a process that goes from left to right, then that's a process where the system is doing work on the environment. So that's work out if it's from left to right. You can imagine that the volume increases during that because there is less volume on the left and higher volume on the right. And if we have a reverse process, meaning from right to left, then we have a case where the system is experiencing work from the environment. So the system, the work is going into the system, and that's why we say work in here. Now we need to find the net thermal energy added to the system, and that will be this term here, the heat in. That's the net thermal energy added. So that happens in this part of the cycle. So this cycle will have three parts, this arrow, and this arrow. Now, if it's a cycle, that means you can start anywhere and end anywhere. So for convenience, let's start here where the pressure is P naught and the volume is V naught. The first process is an increase in pressure, but constant volume. So from here to here. that means that the temperature increases during this process, and that is required by the ideal gas law. And so in this part of the process, this is where heat comes in. So there is heat in this process here. Then in the second part, this branch here, the volume actually doubles. And so we know that work is also done in this process. And then coming back to complete the cycle, we have a shrinking of the volume and also probably a change in temperature. And that is our process. And now we're only interested in the heat in for the first question. So we have to use this bit here. The change in internal energy equals heat in minus work out. So the change in internal energy, because this is a cycle we're talking about for one complete cycle, that's 0. And in this case, let's call the internal energy U sub int. And so if we use the first law of thermodynamics, we have 0 equals Q in is, let's call the heat in Q in and the work out W sub out. So we now have this equation from here. Now we can solve for Q in because that's what we're interested in, and we get this. Now we just have to solve for work out right now, and we can do that from this diagram here. So the work done by the system, work out of the system, is actually the area under the curve. So that's what we said here, the area under the curve. So if it's going to the right, that's a positive work. So that's the area under this. So that's going to be the area of this entire rectangle. So this area here under this bit here. Now that is for this process. It's for this process. For this process, the first process, the volume doesn't change, and so also the area under that is 0, so nothing. There is no effect on the work for this first process. Now for the last process, this process here, let's give that a different color, let's say blue. For this process here, the area under that would be this. And also the direction is going there, so it's a negative work done by the system. So this is negative. So we have to subtract this area. The blue area must be subtracted from the red. And so we will be left with this area here. So we just need to find the area here. But we can do this, we can do that area from geometry, right? Because that's just a triangle there. And so we use the following. We use 1/2 base times height. So base is just, this is base and this is height, right? So the base would be 2v sub o minus v sub o. So that's just v sub o. And height is just 2p naught minus p naught. 2p naught minus p naught. And 1/2 base times height is the area of this triangle. And so that is just equal to this quantity, 1/2 p naught v naught, which is this answer here. As shown in figure 2, two particles, each of charge q, where q is greater than 0, that means q is positive, are fixed at A, which is at negative A, comma 0, and B, which is at A, comma 0, where A is again a positive number in the xy plane. A proportionality constant of the Coulomb's law is denoted as K. Now we need to find the magnitude of the electric field at C. And we also need to find the electric potential at C. And taking note that the potential is 0 at infinity. Let us review some ideas that are important in the solution of this problem. First is the idea of electric field. So we know that the electric field at a given point is just the sum the sum of all the electric fields that are produced by all the charges. So in this case, we have a charge A. It produces an electric field E sub A, and we have another charge B, and it produces an electric field E sub B. Now this is extendable to as many electric charges as we want, but in our problem we only have two, so we only use A and B in this case. And then if we want to find, for example, this electric field E sub A, the vector form is given here. What we have is the proportionality constant times the charge. So this is the charge at A over the square of the distance from A to the point that we're looking at. So the point we're looking at is the point XY, and our charge is at the point X sub A, Y sub A. And this denominator here, this is the square of the distance from XY to X sub A, Y sub A. And here we find that this is just the cosine of the angle of that vector, cosine of the angle for that vector, and here is just the sine of the angle of that vector. That will be clear when we show it in the diagram later. And then here we have E sub B. Again, it's just the same. We just replace the A's with B's. Again, the charge Q sub B and the distance from the point XB, YB, where the charge is located. So the charge Q sub B is located at the point XB, YB, and we are looking for the electric field at the point XY. Then for the electric potential, we recall that just like the electric fields, the electric potential is also just the sum of all the electric potentials due to each charge. And for example, this is the electric potential due to charge A, and this is the electric potential due to charge B. So it's just K, Q over D. So we notice that, of course, here we have a square. Here we only have the first order, the first degree in D. So that's got something to do with the integration, but we will not discuss it here. Here we'll now try to find the electric field at point C due to charges A and B. And the way we do that is we first find the electric field due to A, then we find the electric field due to B, and then we just add them together. So first, we'll look at them geometrically. This arrow represents the electric field due to point B. So it points to this direction. So it points to point C. And this yellow arrow, that's the electric field, and it is made up of two components. The X component is this direction, and the Y component is this direction. Now, the electric field due to point A would be like this. This time it points that direction, and it has this X component and this Y component. Now, this X here, XY, is actually the coordinates of C. So X and here is actually 0, same as X here, it's 0 because we're talking about C. And Y is just the Y coordinate of C, so that's A. So Y here is A, Y here is A. Now, X sub A, Y sub A is the position of the charge A. So X sub A would be negative A, Y sub A would be 0. And the same is true with X sub B, Y sub B. This is now the position of charge B. So X sub B would be A, Y sub B would be 0. And then we notice that if we do this computation, so this one is just the vertical distance from C to A. So this green vertical distance, and Y sub B is just the vertical distance from C to B. So again, this is the yellow vertical distance. And that's just A minus 0, right? So Y minus Y sub A equals Y minus Y sub B equals A. So this vertical distance is just A. And then we look at the horizontal distances. So X minus X sub A, so that's from here to here. Looking at this green horizontal distance, so that's just 0 minus negative A. That's just A, right? So X minus X sub A. And for this bit, x minus x sub b is here, so 0 minus a, so that's negative a. So we just chuck in a negative sign here, and now we still have a there. So this bit is a, this bit is a, therefore this length here would be a square root of 2, because this is a 45-45 triangle, right triangle, an isosceles one. And we know that the hypotenuse is the side times the square root of 2. So that's what we write here. This side and this side is a times square root of 2. And then we know that the charges are q, so q sub a equals q sub b equals q. And then we notice that the electric fields, this electric field and this electric field, its components are this vertical and the horizontal one. We notice that they are symmetric with respect to the y-axis. What that means is that the x components are equal, but in this case they are in opposite directions, right? And that means they will cancel. So this vector component cancels with this vector component. So we are left with the vertical components, but we have two of them, the green, which is from this electric field, and the yellow, which is from this electric field. And so the magnitude of our electric field, of the net electric field, is actually just twice one of them. So we just need to compute one of them. Let's say we compute for E sub A, and let's put that to be E sub Y. So E sub A is just K, so what we have here, K, and the 2 just goes here. Again, that's twice E sub Y because we have yellow and green. And then Q, which is Q sub A, we know that's just equal to Q. Then here we have the distance from the point C to the point A. So this distance, which we already know to be a square root of 2 here. And then this bit here is just the y component. So this component here, because now we already know that these bits cancel each other. So we're left with this one. So y minus y sub a, we already know that to be a. So that's just a vertical distance a. And again, the denominator here is just the distance d sub a, which we again know to be this distance, which is a times square root of 2. And simplifying that, we just cancel the a's, and then when we square this, we have a 2 here, so the 2 and the 2 cancel. So the square root of 2 remains, the k and q remain, and then the square of a, we have the square of a here. So kq over a squared times square root of 2. So that will be our answer. Now let's look at the electric potential. Let's see. And this will be a little bit easier because we already know this relationship here, that the total potential is just the sum of the potential due to A and the potential due to B. And we know that they're the same, and the distance, this distance d sub A and d sub B, we also know that they're the same from here, and that they are just equal to a square root of 2. So we replace them with a square root of 2 here. Now we just add them together, we obtain this. It's just twice kq over a square root of 2. Then we have 2 divided by square root of 2 is just the square root of 2, and nothing in the denominator. And so this would be the correct answer. As shown in figure 2, two particles, each of charge q, which is positive, are fixed at A and B. Again, the lowercase a is a positive number, and this is in the xy plane. The proportionality constant for the Coulomb's law is denoted K. Then, a particle with a charge negative Q and a mass m is placed at C. So here we add a particle, and the charge is negative Q and mass is m. Now we need to find the magnitude of the force acting on the particle at C. The particle at C starts to move from rest and passes through the origin, O. Find the speed of the particle at point O. When the particle at C has an initial speed v sub O, in the negative y direction, so going this direction, it escapes from the influence of the Coulomb forces from the particles at A and B and moves to infinity. Find the minimum value of V sub O. There will be three concepts that will be useful in this problem. First is the definition of electric field. So electric field is actually defined as that vector field such that when you multiply it with a test charge, Q, you get the force acting on that test charge. And the force is defined as the mass times the acceleration. So dv dt here is the acceleration, v is the velocity or the velocity. And this is from Newton's second law. And then we also need to think about the escape speed. And this is the speed at which the kinetic energy is greater than or equal to the potential energy. So that's the minimum energy. So we need to find that minimum kinetic energy that will be greater than or equal to the potential energy. So minimum means they're equal because anything greater than that is acceptable. Now let's first find the magnitude of the force acting on the particle C in here. So again, we use this relationship here. So the force is just the electric field times the charge Q. So the charge in the problem is given to be negative Q, and the electric field, we can find it from the answer of the first problem in this section. So there we saw that the electric field is kq over square root of 2 times a squared. And if we just multiply that with this negative q, and we get the absolute value because we're looking for the magnitude, we see that this is the expression here. And then we simplify that, we get this. So we just replace this with this, and negative q, the absolute value of that is just q. So the correct answer would be this. So here I wrote the conservation of energy. Now let's apply it to this problem. So now we're interested in the conservation of energy between this point and this point. At this point, the kinetic energy is denoted Ke sub c, and the potential energy Pe sub c. Now, it moves towards this point, and at this point, the kinetic energy is denoted Ke sub O, and the potential energy Pe sub O. We are interested in the speed at this point. And so let's try to give values to each of these terms. First, the kinetic energy at this point, because the particle is at rest, it will be 0 because it's just 1/2 m times the square of the speed. So the speed is 0. And so we get this. The potential energy is just the product of the charge times the potential difference, or rather the electric potential at that point. And so negative Q is the charge given by the problem. And this is the electric potential as we know from problem 2, or rather question 2 of this problem. And so we just substitute that. And this is the potential energy at this point. Now, at point O, the kinetic energy is 1/2 mv sub O squared. So V sub O is the speed of the particle at the origin. So that is just the potential, the kinetic energy rather. And the potential energy, again, it's just negative Q, which is the charge, times the potential energy or electric potential at O. And to get the electric potential, we just use what we used in question 2 of this problem. So you can look up that video. And it's just the sum of the potentials due to A and B. And that's just K, Q over the distance. So the distance from A to the origin, which we are looking at right now, is just A. And the distance from the origin to B is also just A. So this is due to A, this is due to B. And their charges are just Q, and the proportionality constants are just K. Rather, constant is K. And so this is pretty simple to evaluate. This is just 2kqa. And so the potential energy at O is just negative 2k q squared over A. Now, we have these values. We plug them into this equation here. That's what we do here. So we just have 0 from here, this from here, this from here, and this from here. And now we're solving for V sub O. So I'm just going to move this to the other side. And that's how we got this bit. And on this side, this remains. Now I can just multiply this bit by 2 and divide by m. And so I can get this expression. And now this corresponds to this. You just get a square root of both sides and you get this. Now let's look for the escape speed of the particle. And that is when the kinetic energy is equal to the potential energy. And we can get the minimum of that by using the equal sign here. So the kinetic energy is equal to the potential energy. We put the absolute value symbols here because often we denote PE, or the potential energy, with a negative value. But in this case, we are looking at their magnitudes. And so we start with the kinetic energy. The kinetic energy of this particle here at C, so at the beginning here at C, the kinetic energy is 1/2 mass times the square of the speed. And it is given that the speed here would be V0. So we put the speed there. So that's the speed that we're looking for. And again, here, the potential energy is just the electric potential times the charge at C. So the electric potential is just V, and the charge is given to be negative Q. And we've already computed V in a previous problem. So that's problem 2.2. So let's just use the value there and plug it in here. So we get V equals the square root of 2kq over A. Then we use this equality. This is the equation that we want to solve for V0. And if we just move around some of the variables, we can solve for the square root, or rather the square of V0. So m here just goes here, and 2 here goes up here. Now we are looking for V0, so we just get the square root of the whole thing. You see that what we're looking for is actually this bit. As shown in figure 3, object A of mass m is moving with speed b on a frictionless surface. Object B of mass 3m is at rest and attached to the end of a spring with spring constant k. The other end of the spring is fixed to a wall. Object A and B and the spring are aligned on a straight line. At time t equals 0, object A hits object B elastically. Now we need to find the velocity of object A after the collision, and also the velocity of object B after the collision. Two key ideas are relevant in this problem. First is the conservation of momentum that relates the momentum before and after any collision, or in fact, any non-collision events too. So what that says is that the sum of the momentums of the first object and the second object is the same before and after the collision. The momentum is just the product of the mass and the speed. So for object A, for example, that would be the mass m1 and its velocity or speed. And for object B, that would be its mass and its speed. And all these before the collision, and after the collision, we do the same. Mass times the speed after the collision, mass times the speed after the collision. And the other relevant idea is the idea of an elastic collision. An elastic collision is one such that the kinetic energy is conserved. So the sum of the kinetic energies of object 1, or object A, and that of object B before the collision must be equal to the sum of the kinetic energies after the collision. Now, we need these two equations because we are looking for two unknowns. The two unknowns are the speeds after the collision. So that's v1 and v2. Now that we have these relationships pinned down, we just need to substitute the values. So for object A, the mass is m. For object B, the mass is 3m. Before the collision, the speed of object A is v, and the speed of object B is just 0 because it's at rest. Now we're looking for their speeds v1 prime and v2 prime after the collision. So here we just used the conservation of momentum. So we just replaced the variables here. And so we get this equation here. And now we get v1 in terms of v2. And now we also use the second equation. Again, the kinetic energy is just 1/2 the mass times the square of the speed. So we replace the variables with these ones here. And so we obtain this relationship. Again, we have v in terms, or rather we have v1 and v2, and they are related by this equation through v, which is the speed of object A before the collision. Here we just need to solve the simultaneous equations that we obtained. So again, we write the equations that we obtained, this and this. And now we notice that v1 prime here is expressed in terms of v2 prime. So we can substitute this expression into here. And so if we do that, we replace the v1 prime with this bit here. And if we just go on with that, we obtain this. So we just copy this side and this bit, and this is just expanded. So that's just the square of a binomial. And then we simplify this equation a little bit more. So canceling the v squareds, for example, and combining the v2 prime squareds, that's 9 plus 3, 12. And then we get this simpler equation. Now we can even cancel the 6's and factor out the v2 prime. And so we get 0 equals v2 prime times 2v sub 2 prime minus v. And that gives us two possible values for v sub 2 prime. One is v sub 2 prime equals 0. And if this is the case, we use this to get v1 prime. And we see that, so we substitute 0 here. So we see that v1 prime is just equal to v. Now, that's one case. However, if you think about that, you have a ball that is the v1 prime that continues to move at the same speed v. So when they collide, object A continues to move at speed v, as if this object here was just a ghost. And in fact, it says here that v2 prime remains at rest because the v2 prime is 0, so object B rather remains at rest. So it's like they collided, this remained at rest, and object A just moved forward at the same speed. So again, object B is like a ghost. And that's clearly not physical. So this is probably not the answer we're looking for. So we look at the other solution. So for this bit here, so the other solution is such that 2v2 prime minus v equals 0. And if we solve that, we get v2 prime equals 1/2 v. And if we have this, we can use this again to obtain v1 prime equals negative 1/2 v. And this is more intuitive because v2 prime has a speed or is equal to 1/2 of v. So that means this object B moves forward the same direction as the original direction of object A, and it moves at half the original speed of object A. And object A now, so v1 prime is the speed of object A after the collision. It now has a different direction, so it bounces off object B, and its speed is now 1/2 its original speed. Therefore, the answer we're looking for problem 1, which is the velocity of object A after the collision, so that's v1 prime, so that's negative 1/2 v, and for object B, that's 1/2 v, so that's v2 prime. After the collision, the spring is compressed. At time t equals capital T, the spring takes the maximum compression L. Now we need to find L, capital T, and the compression of the spring at time t equals capital T over 2. Now let's try to recall a few things that will help us solve the problem. First is the conservation of energy. So at every point in the process, before or after the collision, energy is conserved, and that means that the sum of the kinetic energy and the potential energy before the collision, for example, is the same as the sum of the kinetic energy and the potential energy after the collision. Another is the idea of potential energy stored in an ideal spring. And we know that from physics, and that is just 1/2 kx squared. Here k is the spring constant, and x is the displacement from the equilibrium position. So in our case, the equilibrium position is the initial position. That is when the spring is neither compressed nor stretched. So that is the initial position of our spring at the beginning of the problem. We also make use of the idea of simple harmonic motion in a spring. And just to recap, this is the differential equation that describes the motion of a spring in simple harmonic motion. On this side is the force due to the spring. So this is from Hooke's law. It is just the negative of the spring constant times the displacement from the equilibrium position of the spring. And on this side, it's just the mass times the acceleration. And we know that the solution to this is actually the sinusoidal function with a constant here. And in fact, if we try to get the acceleration given this displacement, so we just differentiate this twice. So we get this term here. And if we differentiate this twice, we see that that derivative is actually a times this angular frequency here, square of that, times sine of omega t. And then we notice that this term a times sine omega t, that's just this here. So we can replace that with x of t. And so we are left with omega squared times x of t. So the acceleration, if the object is in simple harmonic motion, the acceleration is equal to the square of the angular frequency times the displacement from equilibrium position. Again, we're just reminded that A here is the maximum displacement. So it's the maximum compression or stretching. Omega is the angular frequency, and m is the mass of the object. So here we just wrote down what we learned from the previous slide. And then for problem 3, we are asked for the formula for L, which is the maximum compression of the spring. Now, let's think about what happens at the maximum compression and what holds during that. So we know that, for example, the conservation of energy holds, because the conservation of energy will hold any time at any point. And so even during maximum compression, this relationship holds. And also during maximum compression, for example, here, if the spring is at maximum compression, it is about to come back, right? Because if it keeps moving forward, then it was not at maximum compression, right? So if it's at maximum compression, it would have to return to equilibrium position. And so at the point where it is maximum, where the compression is maximum, it is stationary. It is its speed is 0. And so we can use this conservation of energy to solve for how long this compression is. So let's use the conservation of energy, and we know that the energy, the kinetic energy, is just 1/2 times the mass times the square of the speed of the spring, and potential energy of the spring is given here. So let's write them down. So here, this is the potential, or rather this is the kinetic energy of object B at rest. So here, when it is at the initial position, here at equilibrium, it is moving. When this object collides with this, it starts moving at the speed of 1/2 v. We know this 1/2 v from problem 3.2. So this is from the previous video. And 3m is the mass of the object here. And 1/2, well, that's for the kinetic energy. 1/2 times mass times the square of the speed. And then at equilibrium, meaning at the initial state, when the spring is neither compressed nor stretched, the potential energy is 0 because x here is 0. Remember, x is the displacement from the equilibrium position. So if it's at equilibrium, then x is 0, and so we have a potential energy of 0. So this is the initial state right after the collision. Now, at the state of maximum compression, we said that the object actually stops for a moment, and so the speed is 0, and the kinetic energy is therefore 0, but the potential energy due to the spring is maximum. So it is 1/2 times the spring constant K and times the displacement from the original position, or rather the equilibrium position, and that displacement is just L because L is the maximum compression, and we're talking about that time now. And so we have L squared here. Now we just solve this equation for L, and for example, we can cancel the 1/2 here, the 1/2 here. This 1/2, we have a square term here, so that becomes 1/4 times 3. That's why we have 3/4. And then the m remains, and then this v is squared, so v squared. And on the other side, we have L squared and k. And we just move the k down, and now we get the square root, and of course this gives us our L. And therefore from the choices, this is the answer. And we also note that this is the A here in our equation for the harmonic motion, simple harmonic motion. Question 4, we need to look for capital T, and that is again the time when the maximum compression happens. And we will use these equations here, these relationships here, to find capital T. So again, we say that capital T is when the maximum compression happens. And we know that because this is the relationship between the compression and the time, we know that when this is maximum, sine is maximum. That's because A here is a constant. So we need to find T such that sine of omega T is maximum. And what is the maximum value of sine? That's 1, right? And so we're looking for the value of capital T such that sine of omega T is 1. And that happens when the value inside here is pi over 2. So omega T equals pi over 2. Now, we can just move the omega here down here, so in the denominator, and now we have T. And now we just need to find the value for that omega. So again, we use this equation here. So we will just replace the K here with a given K, M here with a given mass, 3M. And if we do that, we get this relationship. So again, the K is just the K, X is just the X, M is 3M here, And this acceleration here, we take it from here, which is equal to negative omega squared x here. So the negative and the negative here cancel, the x and the x here cancel. And so to isolate omega, we just move the 3m here at the denominator. And now we get the square root. So we get omega equals k over 3m. And if we want t, because omega here must be in the denominator here, we flip the numerator and the denominator. So we get t equals pi over 2 square root of 3m over k. And that is this in the choices. Now we need to find the compression of the spring at capital T over 2. And this is not very hard if we already know the constant A here and the omega T over 2. So all we need to do is replace the T's with T over 2. And so let's do that. So here we replace that. X of T over 2 equals L sine of omega T over 2. So we just replace the T with this T here. And here L is equal to A. We already know this from question 3. So we are just going to use it here. And now, the nice thing is we also know what omega T is, right? That is from question 4. So from question 3-4, we know that omega T is pi over 2. And therefore, omega T over 2 is pi over 4. And so we can replace this whole thing here with pi over 4. So it becomes like this. We know that sine pi over 4 is actually 1 over square root of 2. And so that becomes L times this is 1 over square root of 2. And that is just this letter F in the choices. A hot air balloon of mass m is shown in figure 4. The volume of the air bag is V. The mass m does not include the mass of the air inside the bag. The bottom of the air bag is open, and the air pressure inside the bag is equal to the surrounding air pressure, P. The burner sitting on the basket is used to heat the air bag inside. The molar mass of the air is denoted by lowercase m, and the acceleration of gravity is denoted by lowercase g. The air is an ideal gas, and the universal gas constant is denoted by R. The temperature of the surrounding air is T sub O. Let us now list down the quantities that were mentioned in the problem. First is the uppercase M, which is the mass of the balloon without the gas. So it's the frame of the balloon and everything else except the ideal gas that's inside or outside the balloon. And this is fixed. Then we have the volume V, which is the volume of the balloon inside of which is the gas. And this V is the volume of the gas inside the balloon, and this is also the volume of the gas that was displaced by the balloon. So the volume of the gas outside the balloon that is displaced because of the expansion of the balloon. The lowercase m is the molar mass of the gas. It is the grams or kilograms per unit mole of gas. And so this is fixed and this doesn't change. This only depends on the chemical composition of the gas. Then we have P, which is the pressure inside and outside of the balloon. So this is fixed in the problem. This doesn't change. Then we have T sub O, which is the temperature outside of the balloon. And again, the problem is stated in such a way that this is fixed. The temperature outside the balloon does not change because there's an unlimited reservoir of air outside the balloon. So we can think of it as not changing. Then we have some ideas here to remember. The gas temperature inside the balloon can change. So although the temperature outside the balloon, which is T sub O, although that remains constant because there's just a lot of gas outside the balloon, the gas inside the balloon, the temperature of that can change because of the burner. And then as the temperature changes, according to the problem, the pressure and the volume does not change. And so the amount of gas has to give. That means as you heat the gas inside the balloon, there will be fewer and fewer molecules inside the balloon. And so the amount of gas inside the balloon, that is the N, the number of moles, can change. And then we have the ideal gas law. This is to remind ourselves when we are dealing with gases and ideal gases, it is always useful to recall the form of the ideal gas law, this form, which is PV equals nRT. Here, R is the universal gas constant, N is the number of moles, V the volume of the gas, P the pressure, and T the absolute temperature. After the air inside the bag is heated by the burner, the temperature of the air becomes T. And the problem is, find the density of the air inside the bag. So we would like to know the density after the heating occurred. And we are talking about the gas inside the balloon. So let's think about density because that's what we're looking for. That is defined to be the mass of the gas inside the balloon over the volume of the gas inside it. And the volume of that is constant. It's fixed to V according to the problem. That is the volume of the balloon. And for the mass, we're only talking about the mass of the gas inside that balloon. And if we look at the given from the problem, it looks like the way we're going to obtain the mass is through the number of moles here and the molar mass. Because if we recall, molar mass means it is the mass per unit mole. And N is just the number of moles. So if we multiply the number of moles times the unit mass per, or rather the mass per unit mole, then we can get the total mass of that gas for the given number of moles. And this is what we mean. So the density here, we get the mass by multiplying the number of moles of gas inside the balloon times the molar mass. Again, molar mass is the mass of the gas per unit mole. So the mole and the mole here cancel. And now we have this. But this is not in the choices, and definitely N is not in the choices. So we have to express it using another way. And the relationship that we have is actually the ideal gas law. And so let's try to manipulate the ideal gas law to give us a value of N sub in, or the moles inside the gas. So inside the balloon, the ideal gas law can be written as follows. PV, so that's the pressure and volume inside the gas that's given in the problem, or rather inside the balloon as given in the problem. N sub In is the number of moles of gas inside the balloon. R is a constant, and T is given to be the temperature of the air inside the balloon. If we manipulate this a little bit, we can find the value of N sub in, because that's what we're looking for in here. And we see that if we divide that by RT, if we divide this by RT and here by RT, and then we divide again by V here and by V here, we get this expression. So we already have N over V, and that's already almost like this. We only need M to get the density. And so we multiply both sides by M. This is what we get. M times this equals M times this, and this is the density. And therefore, the value of density can be obtained by this expression, which is this. Next, we need to find the buoyant force acting on the balloon. And the buoyant force is the force upward created by the air surrounding the balloon. And that causes the balloon to rise at some point. The way we compute the buoyant force is through Archimedes' principle, which states that the amount of buoyant force is actually equal to the weight of the gas displaced by the balloon. So the gas that is displaced by the balloon is the gas that would have been here in this volume if the balloon did not exist. So because the balloon is here, some of those gas that would have been here is now displaced. And we need to find the weight of that gas that is displaced. So now it's displaced, it's now scattered outside in the fluid, in the air outside of the balloon. And we need to find the mass and the weight of that gas. So again, we stated here, so the weight of something is just the mass of that thing times the acceleration due to gravity, g. So that is the weight of the balloon is, or rather the weight of the gas displaced by the balloon is equal to the mass of the gas displaced by the balloon times the acceleration due to gravity. And again, the mass here, it looks like we can find it using the molar mass and the number of moles of the gas outside the balloon. Again, the molar mass is the same for inside and outside the balloon because it only depends on the chemistry of the gas, but the number of moles could be different. So outside the balloon, let's say there are n sub O number of moles of gas that was displaced. So if we continue, outside the balloon, we are looking for that n sub O. And again, we use the ideal gas. We have PV equals the amount of gas displaced, R times, again, T sub O, because T sub O is the temperature outside the balloon. And again, we're looking at the gas outside the balloon here. So we can solve for n sub O. Now that we have n sub O, we can actually find this quantity. We just multiply by m, and then we also multiply by g, of course. So this is what we get. PV RT sub O, so that's from here, and the m is also from here, and the g is from here. And therefore, this is the correct answer. The next part of the problem goes, the balloon starts rising from the ground when the temperature of the air inside the bag is T sub 1. Now we need to find T sub 1. Now we think about when the balloon starts rising, and that is when all the upward forces equal all the downward forces. So the upward force, the only upward force here is actually the buoyant force, which we computed in the previous question. And the downward forces acting on this are the mass of the balloon itself, excluding the air, times the acceleration to gravity. In other words, that's the weight of the balloon itself, plus the weight of the gas inside the balloon. So those are the two forces acting downwards. So when those forces are equal, meaning the downward forces and the upward forces are equal, that's when we can tip the balloon to start rising. And therefore, the condition is that the buoyant force, which is the upward force, equals the weight of the balloon plus the gas inside it. And we already know the buoyant force. This is from the previous question, question 2. So we write it here. And now we just need to compute the weight of the balloon plus the gas inside. And we know that the weight is just the mass times the acceleration to gravity. So we already know the mass of the balloon itself, which is this capital M. Now we just need to find the gas inside, or rather the mass of the gas inside the balloon. So again, we just write it here. Now this mass, M sub in, so this is the mass of the gas inside the balloon at temperature T sub 1. Again, we use the relationship that that mass is just the molar mass times the number of moles of gas inside that balloon. So that's this relationship. So again, we used the ideal gas law to compute this. And it's the same manipulation from the previous two questions. So we have here PV is the same. It did not change. What changed here is the temperature, because this is now the temperature now inside the balloon is T sub 1. And this is what we're looking for. At what temperature does the buoyant force equal the weight of the balloon and the gas inside it? And we can get an n sub in. Now we just multiply it by m. So that's what we got here. We multiplied by m, and the total thing, the total force or mass is multiplied by g to get the total force downward, or the weight. So now we have this buoyant force and we have this weight here. Now we just need to equate them. And so the balloon starts rising when this buoyant force equals the weight. In other words, this equals this. And right off the bat, we can cancel the g's. Continuing, we had this expression, this relationship, and now we just manipulate it to obtain this. So we just move the m to the other side, and now we want the t sub 1 here. So we flip the numerator and the denominator, and this is what we get. And now the r's cancel, and finally we obtain this, which matches this one. Now they ask us to compute the actual value of t sub 1 if the other values of the variables, if the other variables have the following values as stated here in the question. So we start from what we got from the previous question. So this is what we got from the previous question. And just to have fewer computations, I decided to divide the numerator and the denominator by MPV. By doing that, instead of computing for this here, I get a 1 there. And now in the numerator, I don't even have to compute that. So now I just have to compute that once in the denominator here. Now I just replace everything. And also, we don't have to worry about significant figures here because all of them has 2 significant figures, all of the things in the choices. So we just continue with replacing the values here. And this is what we get when we replace the things. And one tip here is to first sum all the exponents of the tens and then do the cancellations when possible, like the 3 and the 3 here. And for example, if I do the sum for the exponents of the tens, that will be 2 plus 2, 4. And in the denominator, that's minus 2 plus 5. So that's plus 3 and plus 3, 6. So this is 4 here and this is 6 here. So there's a 2 remaining in the denominator. And so that becomes like this, 300 on the numerator. And then here we get the 2 that remained. Then the 3 and the 3 here cancel. So we have 5 and 8.3 and we have 2.9 in here. Now this is 290, this whole thing. Then I just multiplied it here and here. And I noticed that this becomes 41.5. So in the exam, we are not allowed to use calculators. So we want to estimate as much as possible. But this one is not very hard. So 8 times 5 is just 40. So this is around 41.5. But when I do the subtraction, I felt like it might be easier if I round this down to 40. So I do that. And if I do that, if I round this down to 40, that will be 290 minus 40. So I get 250 in here. And the numerator, the 290 times 300 is not very hard. So I just put 8.7 times 10 to the 4th. And now again, I can cancel 10 to the 4th by 100 here. So I get 8.7 over 2.5 times the remaining exponent is 2. So 100. And now 8.7 over 2.5, I could try to compute this precisely, but even before doing that, we noticed that if you have 3 times 2.5, you get 7.5 here. And therefore, this value must be greater than 3 because this is the numerator is greater than 7.5. And so I know that the T1 I'm looking for is greater than 300 because 3 times 100. At the same time, I also know that 2.5 times 4 must be 10, but 8.7 is less than 10. Therefore, this value of T sub 1 we're looking for is less than 4 times 100, so less than 400. And the only choice we have for that is actually letter D in here. Two loudspeakers, S1 and S2, are placed on a plane as shown in figure 5. The X and Y axes are defined as shown in the figure, and an observer is located at the origin O of the XY plane. The speed of the sound is constant and denoted by V. The distances OS1 and OS2 are denoted by D1 and D2 respectively. Let us review some ideas related to this problem. First is that of a wave. A wave would have a source of a vibration, and that source of vibration will determine the frequency of your wave and the speed of your wave. For example, if you have a source of sound waves, the frequency of that sound, which is the pitch of that sound, would be determined by the source from where it's coming from. At the same time, it is the nature of the sound and the medium through which it's traveling that actually determines the speed of that sound. And we know the speed of sound to be around 350 meters per second. And if we want to determine the other quantities, such as the period and the wavelength, we just use these relationships. Next is the idea of constructive interference. We say that two waves constructively interferes if their crests and their troughs align properly, so they exactly align on each other. So for example, if we have this wave here, this is wave 1, and you have wave 2 like this, if they are aligned properly, they just add to each other, and so the crest would be this crest plus this crest, and the trough would be this and this added together. And that happens when, for example, in this case, we have a wave source and another wave source here. And suppose they have the same frequency and the same speed. The waves have the same frequency and the same speed from both sources. And there is an observer here, any point here. And what happens is the wave propagates to the observer. Both waves propagate to the observer. The wave from this source would propagate around D2. The distance is D2. And so let's write it here. And this source would also propagate for a distance of around D1. And that is this. So what happens when we want them to constructively interfere? That means we want their wave cycles to be in sync. That means the waves here must be in sync at this point while they're propagating. And at the same time, the waves here must also be in sync with the next set of wave fronts. And therefore, the condition that we actually want to satisfy when we want them to constructively interfere is that their difference in path length, in this case difference between D1 and D2, must be a multiple of the wavelength of the wave. So integer multiple. And so, for example, if we have 1 there, so it's just one cycle like this. Here there's also one cycle. And the important thing is they align, and they could align if there are exactly n cycles in this region here. And this could also be satisfied if you have 2 cycles. So that's 2 cycles from that source, and that's also 2 cycles from this source. And so if that occurs, then you have waves that properly align next to each other, and so you get constructive interference. Next, we also want to review the Doppler effect. So the Doppler effect happens when the distance between the source or rather the source of the wave and the observer of the wave is changing. So if the distance is changing, we observe a Doppler effect. What that means is that if there is some speed either of the source or of the observer, we will see the Doppler, we will observe the Doppler effect. If the source and the observer are moving apart from each other, they're moving away from each other, then we observe the new frequency. The observer actually observes the frequency to be this. That's just the original frequency times this ratio here. This one is the original speed, the speed of the wave from the source. That's Vs. And u is the speed at which they're moving apart. Now, if they're moving closer to each other, this is the frequency that the observer will observe. What changed is just the sign here. The sign here is now minus. And you will notice that what this means is that this frequency is actually greater than this frequency. And so if they're moving closer to each other, the pitch of a sound, for example, will be higher if they're moving closer. And again, that's because we have a minus sign here, and here we have a plus sign, which means that the pitch will sound lower if the source is moving away from the observer. And of course, if they are stationary, if no one is moving, so u here is 0, and if we do that substitution, we get that the observed frequency is the same as the source frequency. And lastly, we need to remember the beat frequency, and that is just the difference in the frequencies of the two interfering waves. We will not derive it here, but this is a standard topic in textbooks. The first part of the problem reads, initially both speakers are at rest and the x-coordinates of S sub 1 and S sub 2 are the same. They emit sound waves with the same frequency f and the same amplitude. There is no phase difference between their sound waves. Starting from a frequency which is lower than v over d sub 1 plus d sub 2, the frequency is increased gradually. At a certain frequency, the observer first heard the sound with maximum intensity. Find the formula for this frequency. The clue here is that the observer first heard the sound with maximum intensity. Now, maximum intensity happens when the waves constructively interfere. And so we remember that the waves from S1 and S2 constructively interferes when the difference in their path lengths, so the path length, this path length, and this path length, when that difference is a multiple of the wavelength. And so we write it here. So the path length is just d2 minus d1 in this case, and it's a multiple of the original wavelength of the wave. And it is said that the problem says that the frequencies of the waves are the same, and so that also means that their wavelengths are the same. And so we have n here. N could be any integer, and so this wavelength here, we just convert that into the speed and the frequency. We've seen this before, and we know that the speed of the wave here is just the speed of sound v, and the frequency is just the frequency f. And now the other clue, which is that the observer actually first heard the sound. So this can be satisfied with different values of n. But if it is the first time that this happens, then n must be 1. And so we just replace n with 1, and this is what we get. And of course, we can now obtain the frequency here, which is this. And because this is d2 is greater than d1, we can actually flip them around and put an absolute value symbol, and so that we actually obtain this. Next, speaker S1 starts to move at a constant speed u, which is much smaller than v, in the direction of the positive x-axis. We need to find the frequency of speaker S1 heard by the observer. This is pretty straightforward because we have already reviewed the Doppler effect. Clearly, this is the case when the source and the observer are moving apart from each other at a speed u. Therefore, we use this first equation here. And we just recall that these equations are valid when u is much smaller than v. And so we simply have this, and that is this in the choices. A beat is heard by the observer due to the interference between the sound waves emitted by speakers S1 and S2. Find the period of the beat. We recall that we know the beat frequency to be this, and the period is just the reciprocal of that. And so we just solve for this one and get the reciprocal. So let's start by writing down what we already know. So we know that the frequency of of this speaker here, or rather the frequency of the sound from this speaker as observed from O, is this. And we solve this in problem 2. And then the frequency of the sound from speaker 2, because speaker 2 is not moving, it's just F. And therefore, this beat frequency here is pretty simple to calculate. We just replaced the FO2 here with this one, which is F, and FO1 with this one, which is this bit here. We factor out the F, so we obtain this. Now let's just simplify that. And notice we just multiplied this by this denominator here. And so the V's on top would cancel and the denominator would look like this. And therefore, the period, which is just the reciprocal of this, would look like this. And that would be letter C here. Speaker S2 starts to move as well at a constant speed u in the direction parallel to the positive x-axis. A beat is heard by the observer at a different frequency. Find the frequency of the beat. Now we already know how to find the frequency of the beat, and that is given by this formula. And we already know the value of FO1 from the previous problem. And now we just need to find FO2. And from the Doppler effect, again, we can write FO2 as follows. Here, W is the speed at which the source and the observer are getting farther apart. So that's how fast they're moving away from each other. And in this case, we use W, and we cannot just use U, because U is how fast the observer is, or rather how fast the source is moving to the right. But what we're interested is actually how fast this distance here is changing. So this distance is not really, the change in this distance is not really the same as U. And so we use W instead. Now, we also note that W could be computed as the derivative of this length here, which we call R. So the derivative of the length with respect to time is actually the W, which is how fast it is changing, how fast R is changing with time. Now, if we use this and use this, we plug them in here, and then we can just factor out the V and the F. Now we have this. We simplify that a bit further, we obtain this. And now we just need to find W. And the way we do that is, first, we write down the relationship between R, D, U, and this height. So this is the relationship. We just have the Pythagorean theorem. That is, the length of R squared is actually equal to the height squared and this distance here squared. This distance is equal to the original distance, which is d sub 1, plus this distance, which is the distance traveled by the source 1 at time t. So that's u times the time that it traveled. And then we just differentiate both sides with respect to t. So on this side, we get 2r dr dt, and dr dt is the W that we're looking for. And here, this one is just a constant. So when you differentiate that, that goes to 0. And this bit is just this. So 2 times this expression times the the derivative of the inner function, which is just u. Here we just write down the simplified form of the previous equation. Now, we need to get rid of r. So the way we do that is we just plug in the actual expression for r, which is just this length here squared plus this length squared, which is just d2 squared minus d1 squared. And now we make use of the given that u is much, much smaller than v. And therefore, if we try to compute something with u over v, that would be almost equal to 0. So we use this fact, and the way I do that is I divide the numerator by v and the denominator by v. But because the denominator has a square root symbol, so if you divide it by v in here and you put it inside the square root symbol, it will become v squared inside the square root symbol. And so if you move it out of the square root symbol, that it will just become v. So now it becomes like this. This is u over v in the numerator, and in the denominator, I just divided by v squared, because we can again take this out, and that will just be v over v here. So it's nothing. It's not changing the value of this expression. And now we can rearrange this so that this v here could come inside here, so that we have a u over v. At the same time, this v here could come inside here, so we have a u over v. And therefore, it becomes like this. And now we can actually approximate this to be 0 and this to be 0. And so in the numerator, we will be left with this expression. In the denominator, this d1 over v squared would cancel with this bit here. So we will be left with this in the denominator. And notice that v can be factored out, and so the v here and the v in the denominator of the denominator can also cancel, and we are left with this. And now we can substitute the w. We can substitute the w here with this value. Now we just have to plug in the value that we got into the w's here. So we do that here. Now let's multiply the numerator and the denominator by d2, and we obtain this. Now we can factor out u, and this is what we get. And this is very similar to what we already have in the choices. We just remove the absolute value symbol because d2 is greater than d1 anyway. And we see that that's just the same as this.